of the things that happens, as we'll get to, is we're going to deal with this function here. Don't worry about the rest of this junk, what all of these words are. But for right now, there's going to be a formula that talks about what's called compounding interest. All right. So what happens is the more you compound interest, the number of times you compound interest, no matter what, this portion of it approaches a specific value. Okay. As the number grows larger, and we'll talk about this on Monday when we start putting actual numbers together with bank accounts and stuff like that. It's called compounding. You've heard of things that can compound monthly, quarterly, annually, semi-annually, daily, things like that. As things get compounded more, we start to say it's called compounding continuously. And you've probably seen this formula before. And this isn't anything for today, but just you've probably seen this.
Oh, yeah.
I know that
Okay. This was a button under calculator. Okay. It is. There is a lowercase cursive-ish e under calculator. Right. Now, what this value is allowing us to do is that this is for compounding interest continuously. P stands for principal, how much you're inputting, how much you're depositing. R is the rate. The rate is the decimal value of the percentage. T is for the number of years. That's all this stands for. It's super easy. But the reason why I wanted to get into this today because it has its graph. Okay. So what happens is this value of E comes from here. Let's see if this will work. You guys are going to love this. This is one of my favorite videos of all time. This is called Euler's number. Uh-huh. All right. No, this is that. Huh? No, I say it's just creepy. He did another one too. I'll show you. There's a cat. just because this guy's hysterically bad. Where's his other one? Oh yeah. This you're gonna love this one even more. Whatever. The humor of this is lost on you. Your generation is just a bunch of losers. Anyway, so the idea with this is this E value is still can be exponential growth or decay. What happens with it, it's called natural base E. Don't write this out. We'll come back to why this formula is the way it is. What I wanted to do basically today was talk about how you treat E in terms of simplifying, multiplying, dividing, exponent rules, things like that, and then how do you graph it. This looks like it's overly complicated, but it's not. Okay. Remember, E is just a value. If E is cubed, you multiply it by E to the fourth, how many E do you have? 7. Okay, that's all this is. All right. Treat this just like you would a variable. Okay. If you think of the E value as, since it is a number, wouldn't 2 cubed times 2 to the 4th be 2 to the 7th also? Yeah. Treat it the same way. Okay. You have to treat it the same way. We're not pressing buttons. We're not solving for anything. We're just combining. It's basically kind of like a combined like for some of these things. Okay. We will get into how do you use it when we start talking about the word problems. And again, like I said, it's basically banking problems. Right? Money. They're really straightforward. 10e to the third over 5e to the 5e squared gives you how much? 2e or not 2e? Is that the question? Oh, and then lastly, this one is your monomial squared, which means each term inside has to be squared as well. So you have 3 squared e to the negative 4x squared, so this becomes 9. Now, power to power here, what do we have to do? Multiply. So you get e to negative 8x. That e is no longer happy. How do you make it happy? You put it in the basement and sing sweet aspartotes all day long, apparently.
Never mind.
Like I said, all exponent rules here apply. It's simplifying and working with E. It's easy.
No.
Better. I'm gonna roll. It's time to go solo. We're gonna do this. Graphing. Don't write this down. Since E is this weird value of 2 point something, 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 something with a lot of somethings, how are you going to be able to figure out what it is when you multiply or square it? You're not. They're not going to. But what's anything to the 0 power? 1. And what's anything to the 1 power? Itself. Since we know that 1, e to the first power is 2.7-ish, isn't that enough to fudge your way through things? Yeah. So the idea here is when we go to graph these, we're going to be graphing them in this generic form. It's a times e to the rx, where the r value denotes whether or not it's going to be growth or decay. So let's see, y equals a e to the rx. Now r, if r is greater than 0, it's if r is less than 0, oops, it's decay. Yeah. Okay, so had the arrow there. And then the idea is, as we go through them, remembering that growth is going to go dive up to the right. If the a value is positive, the a value is negative. Remember, it went down. It's sloped downward. And then if it's decay, top to bottom or bottom up. That's what the two of those look like. From there, it's pretty simple. So if we have h's and k's, there's really only going to be a couple ordered pairs that you can even work with. It's usually 0 and 1 and the other. So there's graphing of this one is like ridiculously simple. For example, now I just kind of put this one together real quick just to kind of show you that when you're going through these things, if you have y equals e to the 0.75x, is your rate greater or less than 0? So it's growth. Our a value is positive, which means it's going up and right. And then all we know how to do as far as the point is concerned is that the only value we can plot legitimately is when x is 0. What's anything to the 0 power? 1. What's 2 times 1? 2. Okay. Since I know that there's no h and there's no k here, I know that my horizontal asymptote is still at 0. It hasn't moved. And then that's really all I can draw.
That's great.
It's crazy. Okay? It's crazy. Pace yourself. Right? Same idea. Let's try it with a h's and k's. All right. When we do h's and k's with this stuff, let's put a coefficient in front. Let's make it more fun. Let's put a 3 there.
Oh my God.
3 times e to the negative 0.5 times quantity x minus 2, all plus 1. As we go through these things, we're going to follow the exact same process, except with these, there's a lot less ordered pairs to pick. It's really just one, and we have to understand direction. So with this one, excuse me, what's our a value now? 3. What's our rate?
Negative 0.5.
Negative 0.5, yeah, so it's negative 0.5. So is that growth or decay? Decay. All right. Our h value?
Negative or positive.
Positive 2, good. And our k value?
Okay.
All right. All right, so same idea. It's decay. Since this is decay and the a value is positive, it means it's moving from top left down to the right, okay? The only ordered pair that I can plot for the parent function for this is, well, the horizontal asymptote at 0, and 3. The rest of it, you have to go with, well, I know it's got to be diving from the top down, just because that's how the k goes. So parent function would probably look like this. To that ordered pair of 0, 3, where does it get shifted to?
Down to, up to the right.
How about right 2, up 1? Because horizontal goes left and right. So if our one ordered pair, maybe we should do this again. For our parent function, we know our ordered pair is at 0 and 3. Has to be. So the shift there's your shift. Where's your new asymptote? 1. The new horizontal asymptote would be at 1. And the ordered pair there. I'll just make the dot bigger. It looks like it hit it then. Question about this came up yesterday when we had stuff like this where the parent function and the shifted function looked as if they intersected or one of them ran into the other's asymptote. In this case, notice how the parent function runs into the asymptote of the shift. That's okay. Because remember, the parent function is just there to give us a visual representation of what it's going to look like when it's moving. All right, so it makes no difference. All right, it makes no difference. The other one, I think yesterday there was a problem where there was no vertical shift, so they both shared the same horizontal asymptote. That's perfectly fine as well. It's not a big deal. Right? It's absolutely not a big deal if they share asymptotes. So, but that's again, when we go to this one on our vertical asymptote is at y equals 1. Our domain is all real. And our range is going to be y is greater than 1. Sweet. It's fun.
If I get that stuff in my head for the Christmas speaker on, I don't want to come back here.
I'll get over it.
I won't.
I didn't have much with this. This was a pretty easy Friday. Let me grab my book, see if this works. I think it'll work. I don't know. I think some of those might be the word problem we didn't talk about because I don't want to do those yet. I'll save those next week.
Yeah.
1832. Yeah, that's good. 1560. That's good. Oh yeah. Honestly, you should be done with this by the time you walk out of here. Yes, sir. This is 18 through 32, every other even. These are just evens. These are simplified, like exponent rules. These are, is it growth or decay? And those are a graph. All right? Yes, ma'am.